Is about inelastic collisions. The difference between inelastic collisions and elastic collisions is that inelastic collisions does not conserve kinetic energy, and also for an inelastic collisions, the two objects tend to stick together rather than bounce off of each other. So here's an example of an inelastic collision. The momentum is still conserved, but the kinetic energy is not going to be. Now, I just realized this recently, but if you go and you play that simulation in reverse, then an inelastic collision, go backwards, is really like an explosion in reverse, because if you can go back in time, these two things that are now together would split apart violently. So there's a YouTube video I recommend if you watch fireworks in reverse. You can see something like that. And you'd have things that are basically coming back together. Alright, so let's do an application. Oops, wrong video. Wrong page. Here we go. So an application problem of an inelastic collision. First, let's write down our key concept. Inelastic collisions do not conserve, no conservation of kinetic energy. Kinetic energy is not conserved. But momentum is conserved, so you still have this rule. Initial momentum is equal to final momentum. And generally, when you have an inelastic collision, things stick together. Or if you can think of the situation of an explosion, the things were actually stuck together before the explosion. And those are our main rules here. Let's look at an example question. A 920 kilogram sports car collides into the rear end of a 2,300 kilogram SUV at a stoplight. Let's draw a quick picture. So before we had the SUV at rest, the 2,300 kilogram SUV, mass B, and the 920 kilogram car was headed towards it. Now afterwards, they collide and then they skid, and we were actually given the distance of the skid marks of the two cars that are wrecked. So the distance of the skid in the road was 2.8 meters. So this question is both a momentum question and also an energy question. If I split this segment over here, I like to use green when we're doing energy problems, so it's green energy. That never gets old. So the coefficient of friction was given to be 0.8 between the road and the tires. So there was work done coming to a stop. So the work done is going to be equal to the force applied times the distance traveled, which we know. And the force would just be the friction that was used to slow it down. And we know that friction is represented by mu times n, and in this case, set a cosine of, that's going to be 1. We can figure out how much work was done to bring these cars to a stop. Now, whatever amount of work that is, that must be equal to the kinetic energy at this point. When we had the collision, after the collision we had some kinetic energy forward, that has to equal the work to stop the two cars. So then let's find out how much that is. So let's plug in our values. 0.8 for mu. Now normal force, that's just going to be the same as their weight. So the weight is going to be the sum of both masses, ma plus mb, times g, which is 9.8. All of that times the distance d, and we get a value of 7,100 joules. Now that is equal to the kinetic energy at the after the collision. So then we go back and we do momentum work, and we can make the connection between this value and its energy, which can yield how fast it was going, to find out how fast the car was going initially. So let's go over here. We'll do some momentum work. Initial momentum is equal to final momentum. So that means I'm going to say mass A, velocity A, which is the value that we're going to be trying to find out, velocity A being the car before the collision, plus the momentum of the SUV was 0, so we don't need anything there. That has to be equal to the final mass when they're stuck together, mass A plus mass B, times the final velocity. So then we will have an expression from our kinetic energy formula here. So that's also going to be the kinetic energy when the two cars come together, cars A and B. So that can give us VF. So we're going to use that to get VF, and I'm going to have to slide down the page and get us some more room. That number. Well, the number for kinetic energy was 70,700 joules, and that has to equal 1/2 the mass, big M plus little m, mass B plus mass A, times velocity final from A and B squared. And from our momentum equation, we got that MAVA equals MA plus MB, all times the final of A and B. So if we can take this value somehow and substitute it in, then we can solve for VA. In the end, what we want is VA. Okay, so let's get an expression for V final A. So to get rid of this 1/2 MB plus MA, we're going to multiply by the reciprocal. So we're going to get the kinetic energy of A and B. I'll substitute the numbers later, but the kinetic energy of A and B times 2 and divided by MB plus MA, remember we're multiplying by the reciprocal, is going to be equal to V final of A and B squared. Now we're going to take that value and substitute it in over here, because what we really want is VA.